This video is all about L'Hopital's rule, and what we use L'Hopital's rule for is to evaluate limits that are indeterminate. And what I mean by indeterminate is that when you find the limit, you end up with something like 0 over 0 or infinity over infinity. So let's say we're given some limit, x approaches some value a, and we are trying to evaluate the limit of f of x over g of x, so some fraction where we have two functions, you could say. What we're allowed to do with L'Hopital's rule is keep the limit, but we're going to have the derivative of the top and the derivative of the bottom. Now notice, I'm not doing the quotient rule here. We're not doing the low-d high and high-d low. We are literally looking at the top of the fraction and taking the derivative, and then taking the bottom of the fraction, and taking the derivative. This then gives us something that hopefully is an evaluatable limit, so it's no longer indeterminate. If you end up with something that is still indeterminate, you're allowed to do it again. So you can keep doing the derivative of the top, finding the derivative of the bottom, keep that limit, and go until basically eventually you get something that is not 0 over 0 or infinity over infinity. So let's do some examples. All right, so in this problem here, we've got the limit as x approaches 0, 2x over the tangent of 4x. And some of us might be able to look at this and say that the top is going to be 0 when I plug it in and the bottom is going to be 0 when I plug it in. But we actually can't just write it like this for our AP test and for our assessments in class, because this isn't really proper notation, because that's not how limit laws work if you have the bottom function approaching 0. Because that's undefined, right? And so we're not allowed to just say, oh, I guess it's undefined. So what we have to show is that the limit laws stay true. So that the limit of the top function as its own piece, yes, if I plug that in, I get 0. And that the limit of the bottom function as its own piece would also be 0. So if we plug in 0 into this, we get the tangent of 0. That's going to be 0 over 1. So that's still 0. So now that we've shown this aspect, that them separately as separate limits are 0, that's when I'm allowed to say, okay, 0 over 0, not great, indeterminate, let's use L'Hopital's rule. And I like to write a little LH to say, like, I'm doing L'Hopital's rule, but you don't necessarily have to do that. You can just jump right into it. So what we're going to do in order to actually use this rule is we're going to find the derivative of each piece. So the derivative of 2x is going to just be 2, and then our derivative of the tangent of 4x, we're going to remember those rules. It's going to be secant squared of 4x, but chain rule says multiply by the derivative of the inside, so times a 4 there. So now we've got this new limit based on the derivatives, and if we were to plug in 0, we'll keep a 2 up top because there's no zeros, and we're going to have 4 times 0 inside of the secant. So now we need to think about, well, what is secant really? That's 1 over cosine, so I'm actually going to throw that up here and think to myself that the cosine at 0 is 1, so that means we've got 2 times 1, and 2 over 4 is 1/2. All right, let's take a look at another problem. So again, I've got this limit. If I look at it, I could see, plugging in infinity, I'd get infinity over infinity. That's problematic, right? But we can't just write that. So we have to say that the limit of the top would be infinity, and that the limit as I approach infinity of e to the x, some huge number, e to the infinity, that's essentially infinity, right? It's such a large number. We're talking abstract here. That's infinity. And that infinity over infinity is indeterminate. So we can't just say this. So let's do L'Hopital's rule. L'Hopital's rule says let's take the derivative of the top and the bottom. So the derivative of x up top here is going to just be 1. And the derivative of our bottom piece is going to stay e to the x, because the derivative of e to the x is e to the x. So now if we go to sort of plug in infinity, I've got 1 over e to the infinity, which is 1 over such a huge number that that's essentially 0. As we're approaching infinity in the denominator, we are getting closer and closer and closer to 0. And remember, limits are talking about approaching. So even though it's not quite 0, it's close enough that we count it. So that is going to be our answer here. Now this problem here is actually a great example of a rule that we can sometimes use where with L'Hopital, you can actually keep doing the derivatives. You can keep doing L'Hopital's rule as many times as you need to. And in this problem, we only had to do it one time, but sometimes you start where you have a problem as you go to infinity and you have like 3x cubed over e to the 2x or something like that. So let's pretend this was our problem, just to give another example. If we go to do L'Hopital's rule once, and we've proven that we needed to, as I've shown up here, then we would go to do the derivative, and we would get 9x squared over 2e to the 2x. And this would still be infinity, and so we would have to show again that all of this is infinity over infinity, and then we could do L'Hopital's rule again. But what we're allowed to say is if we can sort of predict what's going to happen after enough derivatives, I can actually say pretty confidently that eventually the numerator will become just a number. If I do the derivative again, I'll get 18x, and then I do it again, I'll just get 18, so just some number. But the denominator is always going to have some e to the 2x piece, because every time you do the derivative, you're still going to have that e to the 2x part, and you'll just keep multiplying by 2, but you still have that e to the 2x. And so no matter what, we can say pretty confidently that this is eventually going to become 0. So we could do L'Hopital's rule a bunch of times, and we would still have some number over infinity, and that is 0. So on a multiple choice question like this, you don't have to show all of the L'Hopitals that you did. You can just jump straight to the part where you say, I've got number over infinity, so that must be 0. Let's try another problem. So in this example, again, we're going to infinity. So let's check natural log of infinity. Sure, that still seems like infinity. And then if we plug it into 2x, also infinity. So that is indeterminate. Let's use L'Hopital's rule. So L'Hopital says, let's do the derivative of the top. So natural log of x, the derivative is going to be 1 over x. And then the derivative of the bottom is just going to be 2. If we simplify this, that's really going to be 1 over 2x. So if we now plug in infinity, we're actually going to get 1 over infinity, which again, as we just saw in that last problem, is going to be so close to 0 that the limit is approaching 0 as we approach infinity. All right, this next one's got a little bit of spice to it. So if we start out by checking that each separate limit is problematic, right? We would have 3 times 1 minus 1, that's going to be 0. Now, the denominator here throws some people a lot. So when I plug in 1, I've got the natural log of 1. That's really saying e to the what is 1. So e to the 0th power is 1. So that's why the natural log of 1 or the log of 1, whatever the base, is going to just be 0. So 0 over 0, that's indeterminate. So let's use L'Hopital's rule. That means we're going to find the derivative of the top and bottom separately. Remember, we're not quotient ruling this. We are purely just finding the derivative. So before I go to do the derivative, I think it's actually going to be easier to rewrite our original numerator as 3x minus 3. And so now when I go to do the derivative with 3x minus 3, it's just going to be 3 up top. The natural log of x, derivative of that, is going to be 1 over x. And so let's simplify this. We'll get x approaches 1. That's just 3x. And what I'm doing here is, in my head, kind of multiplying by x over x. And so that's where this denominator piece cancels out. So we're just left with 3x. And so now if I plug in 1, I get 3 times 1. And that is going to be 3. All right, I want you to actually pause the video, try this problem out, and then come back in a few minutes and see if you got what I got. So to save time, I've just written the 2 separate limits out. So here we're going to get infinity when we plug in to e to the x, and 2 infinity squared, also infinity. So this is indeterminate. Let's apply L'Hopital's rule. So we're going to do those derivatives. All right, so I've got that written out. So now if we plug in infinity, we're going to get infinity over infinity again, but we can't just write it like this, so we've got to do that good notation that says check the limit of the top and the limit of the bottom. So what we're actually allowed to do if this happens is we can just do it again. We can do L'Hopital's rule as many times as we need until we get something that is determinate, something where we can actually apply the limit. So again, I'm going to differentiate the top, differentiate the bottom. So now if we plug in infinity, we've got huge number up top and 4 in the denominator. This is no longer a case where we can apply L'Hopital's rule. And so this is just infinity, or we could say DNE. If it's multiple choice, you'll see one of these, not both. And so that would be our final answer here. All right, let's do one more problem. So if we are to check each of these limits, I'm thinking to myself, e to the 0, that's going to be 1, minus 1, minus 0. So that all would be 0. So that one's kind of a pain to do, but we got to check it nonetheless. And then our denominator, also going to be 0. Okay, so this is a 0 over 0 problem. That means let's do L'Hopital's rule. So I want you to pause here, try to finish this problem, see what happens. All right, so I had to do L'Hopital's rule 2 times here. And again, showing this notation that we've got the 2 separate limits equaling 0 tells us that we're allowed to use L'Hopital's rule. So now if we plug in 0, we're going to get 4e to the 0 over 2. E to the 0 is just 1. So we've got 4 over 2, which is 2. So that is our final answer here. The last thing that I want to go through today is really important, and that is, when do you actually use L'Hopital's rule? Because sometimes we jump into it a little bit too prematurely. So I want you to look at these 3 examples here, A, B, and C, and determine which ones of these should we actually use L'Hopital's rule for. So looking at these 3 examples, if I plug in 0 into A, I would get 0 up top, sign of 0, but in the denominator, 0 minus 1 is not 0. So this would not be a L'Hopital's rule. This would just be 0. So this one is not for L'Hopital. Example B, if we take a look at this, if we plug in 2 into the numerator, sine of 2 is just going to be a number. I don't know what it is off the top of my head because we think in radians more, but that's not 0. In the denominator, we would get 0. So this would actually just be a limit that does not exist, not a L'Hopital problem, only if it had been 0 over 0. So not L'Hopital. Our last example, if we take a look at it, if we plug in 2 into the top, we'd have sine of 2 minus 2. Okay, that's 0. And if we plug in 2 into the bottom, I've got 2 squared minus 4, which is also 0. So again, we'd want to show that process that each limit is separately 0, and then we would use L'Hopital's rule. So this one is a L'Hopital problem.